This video series goes through the daily problems in this maths calendar that is published by the American Mathematical Society. You can either purchase it through their website or via Amazon. Today's problem is to find the area of the outer equilateral triangle, given that the inner equilateral triangle has got area 9. First, we establish that these three triangles are the same. Because the red triangle is an equilateral triangle, we were told that the three angles are the same, and the angles of a triangle must sum to 180 degrees. Therefore, since the three angles are the same, each is 60 degrees. The same is true for this inner triangle in blue because it too is an equilateral triangle. We were told that its side lengths are the same, therefore it has got 60-degree angles too. If that's 60 degrees and that's 90 degrees, then the angles sum to 180 degrees, so this angle is 30. If this is 30 and this is 60, that's 90 in total, and a straight line has got an angle of 180 degrees, so this angle here must be 90 degrees. If that's 90 and that's 60, then this one must be 30. If this is 30 and this is 60, then this is 90. And if this is 90 and this is 60, then this one must be 30. And the same argument could have been applied here. 90 degrees, 60 degrees here, this one must be 30. So all these three triangles here are the same. We need to work out how much longer the side length of the red triangle is compared with the side length of the blue triangle. So let's call the side length of the blue triangle x, and we want to find y plus z. Method 1 solves this problem by using known values for sine and tan of 60 degrees. If we look at this triangle here, with the right angle here, we see that tan of 60 degrees is equal to opposite divided by adjacent, x divided by y. If we look at this triangle here, we see that sine of 60 degrees, with the right angle here, sine of 60 is opposite over the hypotenuse, so x divided by z. Tan of 60 degrees is the square root of 3, therefore x divided by y equals square root of 3, or rearranging y equals x divided by square root of 3. Sine of 60 degrees is the square root of 3 on 2, half of the square root of 3. Upon rearranging, we therefore get that z is equal to 2x divided by the square root of 3. This means that the total side length of the red triangle, being y plus z, is equal to this plus this. 2x plus x gives us 3x, all divided by the square root of 3. In other words, this is the square root of 3, so y plus z is the square root of 3 times x. The area, if the side length increases by a scalar, the area increases by the square of that scalar. The square root of the square root of 3 is just 3, so the area of the outer triangle is 3 times as large as the area of the inner triangle. Since the inner triangle has area 9, the outer triangle must have area 27. The answer to today's problem is therefore 27. Method 2 starts by adding this extra line here to form an equilateral triangle here, where the side length of the blue triangle is now the height of this equilateral triangle here. Tangentially, there are two ways to draw this line. One is by seeing that this angle here is 30 degrees, as we worked out on the previous page. And so if we add an extra 30 degrees here, then we see that this line bisects this 60-degree angle here, goes straight through the center of the base here, and comes out here. Alternatively, we simply say that if this length from here down to here is x, then we just measure from here out to here a distance of x, and we join up these 2 points here. By symmetry, the distance from here to here is the same as the distance from here to here. Indeed, on the previous page, we explained why all these three triangles here are the same triangle. Therefore, the area of the outer triangle is equal to the area of the inner triangle, which is 9, multiplied by the square of the ratio of the length of the outer triangle, which is x plus x on 2, divided by the length of the inner triangle, which is h. Of course, by length, I mean side length. From the previous page, we know we have a right angle here. We can therefore apply Pythagoras' theorem. The hypotenuse is x, so x squared is equal to x on 2 squared plus h squared. In other words, x squared equals 1/4 x squared plus h squared. Bringing a quarter x squared to the other side gives us 3/4 x squared equals h squared. And bringing h squared to the left-hand side and 3/4 to the right-hand side, we get x squared divided by h squared is equal to 4 on 3. This can be substituted in here, giving us that the area equals 9 times 9 on 4 times 4 on 3. 9 times 9 on 4 times 4 on 3, the 4's cancel. 9 divided by 3 is 3, 3 9s are 27. Of course, this is the same answer as before. Indeed, the reason we know the special values for sine and tan of 60 degrees is by essentially the same diagram involving an equilateral triangle. This was discussed in our video on 8th of January, where we used an equilateral triangle to find the special values for sine 30 degrees, cos 30 degrees and tan 30 degrees, and exactly the same diagram allows us to read off the values for sine, cos and tan of 60 degrees.